So good. All right, why don't we, this meeting is being live streamed. That's good news. Got it?
Oh, I just want to add one more thing, Jim, if you don't mind.
Please.
Everyone, if you look to your left on that wall, all of those images that look like Hubble images are images that were done by our own members. Some of them in places that are light polluted, others in remote areas, and they are terrific. And don't remember to take a look at those before you leave tonight.
Yeah. At the end of the presentation, after questions, we'll turn the lights on. We'll explain this wall here and take a look at those pictures. They are extraordinary images. All right, it's time, John.
Okay. Hello, everyone. Good to see you. I see you all. Tonight's speaker is Dr. Andrew Rivkin from James Hopkins University Applied Physics Lab. He studies asteroids, and he searches for traces of water and organic materials on those asteroids. He is also a co-investigator team lead for NASA's Double Asteroid Redirection Test, or DART mission. So welcome, Dr. Rivkin. Thank you.
Thank you. It's a pleasure to be here. And can you just remind me, because I can talk about this stuff forever, and I don't have forever. So how remind me how long the talk should be.
Well, we normally have a talk about 45, 50 minutes, leave room for questions, and cap it off on an hour. So hopefully the skies will be clear tonight. We'll get some observing into.
That sounds great. So thank you for having me. I'm sorry I'm not there in person. I certainly have been to New Jersey many times. I have cousins in New Jersey, of course. I grew up just across the border in Rockland County, New York. So like I said, I'm sorry I'm not there with you in person. So tonight I'm going to talk about the mission that was just mentioned, the Double Asteroid Redirection Test, which is NASA's first planetary defense test.
You hear back there, okay?
And it's great to see everyone here with me spending this Saturday night. So anytime that you see a shooting star, and I'm sure everyone has seen a shooting star at some point, you're witnessing an impact, a piece of an asteroid or a comet that's coming in and hitting the Earth. Hundreds of tons of material hits the Earth every single day, mostly in the form of these tiny shooting stars. Most of that material that you see when it's a shooting star is only a millimeter in size or smaller, so like a grain of sand or so, just a gram or two of mass. And it comes in, it burns up in the atmosphere. That's what makes the light the shooting star, and stays up there or burns up completely. So those are not dangers. We're happy to see those either inside of meteor showers or if you're just out on a dark night. Sometimes larger things come in, every year or so, we get 3 or 4 objects, maybe about the size of the chair you're sitting in, that hits the Earth. I can't tell if that animation on the upper right is working or not. It's supposed to, but these get captured sometimes because they happen often enough. One of them hit in upstate New York, or slightly upstate New York, in 1992 when I was in graduate school. Some of you older folks might remember. And basically it was occurred on a Friday night. People were watching high school football and had their big clunky 1992 era video cameras videoing their kids at the games, and a lot of them caught video of the impactor, which is again up there in the upper right. The largest piece that was picked up was about 30 centimeters in diameter, so that lower right. If you're not familiar with the metric system, I'll try to do the conversions on the fly. It's about a foot. And it hit that car. This poor young woman had her car struck by a meteorite. It totaled the car. But she sold the car to go on tour, and she bought a new car with the proceeds. So these happen every again, a couple times a year, something about the size of the chair you're in. And as long as you're not directly, as long as you're not so unlucky as to have your car hit by it, again, these are not things we tend to worry about. They're not super dangerous. About 10 years ago, something larger still hit the Earth. This was over the city of Chelyabinsk, which is in Siberia, in Russia. And a lot of Russian drivers have cameras in their dashboards to record what's going on in front of them. And so once again, there were a lot of images of this impactor. This is something that's about the size, and I'm terrible at judging this sort of thing, maybe about the size of the room you're in. It exploded over the city, and it caused damage in a lot of the surrounding towns. So here, things that are the open circles are just nearby towns. The ones that have yellow where pieces were picked up, the ones that are orange and red had some damage. Usually the damage was in the form of broken windows, because people would go see this big flash in the sky, they'd rush to the window or rush outside to see what had happened. And then about 1.5 minutes to 2 minutes after the flash, a shock wave came through, broke all of the windows, and about 1,000 people were hurt from flying glass. So this is starting to get to be the size of an impactor, about 20 to 25 meters. Now we start to want to pay attention to. When you get bigger still, obviously, you get bigger and bigger consequences. I don't know how many of you, and I guess I can see the folks, I can make this audience participation, how many of you in the room there have been to northern Arizona and have seen Meteor Crater?
No hands up at this time.
No hands.
They're planning on
okay.
it, though.
That's okay. It's pretty cool. Northern Arizona is a great place to visit. There's lots of great stuff. Lowell Observatory, which is another beautiful old observatory that you can tour. So on the left there is the crater that was left by an impactor that was about 50 meters in size, 30 meters in size. It was made out of iron metal. And it left that, very impressive kind of 1/2 to 3/4 of a mile wide crater. On the right there are overlaid on that image of Arizona the zones in which that kind of impact would have certain effects. Within about 10 kilometers, or about 6 miles, there would be a fireball that would be very, very bad to be near. Out to, I think that's sort of 18 to 20 miles, 24 kilometers, large animals would be killed or wounded, and all the way out to 40 kilometers, which is a little less than 30 miles, you have hurricane force winds. Like I said, I live in Maryland. Maybe I said this before some folks came in. So of course we think about what happens if something happens close to where we live. If this impact were to occurred instead of tens of thousands of years ago in the desert of Arizona, if it occurred today in Washington, D.C., it would leave a crater about as big as the tidal basin here on the left that you can see. That's this body of water between the Washington Monument and the Jefferson Memorial. And then if you take that same map with the damage and you overlay it on the DC area, you see that I live kind of near the edge of the green and the blue there, kind of the edge of where the large animals are in trouble and you only have the hurricane force winds. So naturally, this is something that people want to think about and imagine, is this something that we need to worry about? How much do we need to worry about it? Is there something we can do about it? And this is the what led to the field of planetary defense. People looking and finding asteroids out there, people understanding that there are craters on the Earth that were caused by impacts, seeing this impact over Siberia about 10 years ago and wondering what's out there and what can be done. Another big factor was determining that the dinosaurs died because of an impact into Earth, and that impacts probably led to a lot of extinctions throughout history. So the United States has a plan for how to deal with asteroid impacts, near Earth objects, as they're called. and there are several goals in this plan. The first one is, you'll be happy to know, is underway. People are looking for asteroids. People have been looking for asteroids for decades. There are search teams that are finding what's out there, that are determining their orbits, that are characterizing what's out there and figuring out the sizes and compositions. But that is only one of 5 goals of the national plan. The people that have done the searches have been able to come up with some numbers. About once a year, we get hit by something that's 4 meters in size. That's about a yard. I'm sorry, that's about 4 yards. So about 12 feet. These are in that size range where there'll be a flash, maybe some things will come down. If your car is parked somewhere, unluckily, maybe your car will get hit, but for the most part, we're not worried about these. And that's good, because there's a lot of them. There's 500 million of them out there, we think. And we have only found a very small number of them. So the fact that they're not really dangerous is good. On the other end, at the 10-kilometer size, which is about 6 miles, that's about the size that we think the impact killed the dinosaurs. Those don't happen very often, which again is very, very good. We think maybe every 100 million to 200 million years we get hit by something of that size. We think we've found all of them that are out there. There's only 3. So we think we're good there. To go down one more size step to a 1 kilometer in size, those hit more often, every 500,000 years or so. It would be very bad if one of those hit. Not as bad as, it wouldn't wipe out kind of mass extinction on Earth, but it would cause enough trouble that we might have to worry about whether agricultural would kind of collapse for a few years, whether you end up with a nuclear winter type scenario without the radiation. But again, we think we've found basically everything out there that's that size, so we know none of those are going to hit. In fact, we don't know of any asteroid that is going to hit us, so we're in good shape there. It's these middle 2 categories that we're starting to think the most about. Objects of about 160 meters in size that would potentially make a very big crater, bigger than what we see in Arizona. And if that were to hit a city or a region, it would be bad for that city or state. There would be mass casualties for sure if we didn't know it was coming. And while they don't hit terribly often, every 25,000 years or so, we haven't found most of them. So I'll stay with the New Jersey theme. If you've been to Atlantic City, you know that if you play roulette, just because a number has come up doesn't mean it's not going to come up again very, very soon. So while people with the telescopes are looking and finding what's out there, there's also been a desire to figure out what we can do if we find something of that size that's incoming. Asteroid impacts are basically the only natural disaster that we can predict far ahead of time. We can predict potentially years or decades ahead of time, and that potentially we can completely avert through human intervention. And that goes to this third goal of the United States plan, which is deflection and disruption and mitigation. And that's what I'm going to be talking about for basically the rest of the time here. And that's what the DART mission is all about. So if we were to find something incoming, we think we have 4 different options for how we might deal with it if we found it today, using today's technology, not depending on anything to be developed. This figure over here on the right shows that depending on the amount of warning time we have and depending on the size of the object where we find, there are, that's the different things that might be our first choice. If something is small enough, then we would just tell people, hey, when you see a big flash, your windows might break a minute or 2 later, so stay away from the windows or you might get hit by glass, because it's going to be cheaper to replace every window in Chelyabinsk than it is to send a space mission to try to stop this thing. So below a certain size, that's just going to be our plan A. Just don't worry about it. Prepare like you prepare for a hurricane, wait it out, and then we'll clean up afterward. The second option, which is of course in all the movies, from Armageddon to Deep Impact, I admit I haven't seen Don't Look Up, is a nuclear deflection, using some sort of nuclear device that would launch. It would come close by the asteroid, and kind of like in this cartoon here on the left, would detonate a little bit far away, and then the shock waves from the nuke, the heat from the nuke would vaporize part of the asteroid and push it off of the orbit that intersects the Earth, so that it misses the Earth. But nuclear explosions are in space are against international law. You cannot test this because we have decided through the UN reasonably that we don't want to be testing nuclear weapons in space. So we're looking, of course, for other options. Another option, which is kind of neat and very elegant, is something called the gravity tractor. This uses the fact that every mass attracts every other mass in the universe if you can get them close enough together. So for this idea, you'd build a massive spacecraft, you would park it very, very close to the asteroid you're worried about, and then you would let the gravity of your spacecraft attract the asteroid. And since you can control the spacecraft, you'd kind of tug the asteroid out of the way like that. As you might imagine, this really works best with very small asteroids, and it works best if you have a lot of time on your hands to make it work. So the last option, and the one that DART is something called a kinetic impactor. And the kinetic impactor is very simply you ram your spacecraft into the asteroid you're worried about. And you use the momentum of your spacecraft, the mass and the speed you bring with you, to change the momentum of the asteroid you're worried about. And again, so that you miss, so that the asteroid misses the Earth. This is thought to be kind of our second best or second most capable option right now, and so the one that we want to try out. And the community of folks who look at these problems, when they meet and when they do studies, they agreed that about 10 years ago they published a study with the National Academy of Sciences saying the first thing we want to do is try out a kinetic impact. So this is a one-sentence summary of the DART mission. We launched last November from Vandenberg Space Force Base in California. We are going to arrive this fall in September at our target asteroid, which is a double asteroid, which is why it's the double asteroid redirection test. The main body is called Didymos. Its moon is called Dimorphos, and we're going to hit Dimorphos with our spacecraft. We're carrying a CubeSat, which I'll talk more about all of these in a little bit. DART is going to come in at 14,000 miles an hour, so very fast, and it's going to give Dimorphos a little bit of a push, and that's going to change its orbit around Didymos. And then after that impact, we're going to watch the results from Earth using ground-based telescopes, potentially like the ones you'll be seeing tonight. So our three overall goals, very simply, are up there in the upper right. Target the Didymos system, impact Dimorphos and change its orbit period, and then measure that period change from the Earth. So why are we going to an asteroid moon? There's a lot of words on this, and I'll try not to bore folks with lots of words, but basically we don't want to give asteroids too big of a push if we push them. We think that rather than being a single brick or a single rock, we think that those asteroids out there are more like flying gravel piles. And if you give them too much of a push, it would be like throwing a snowball that's too loosely packed. It'll just come apart in your hand. So we think you just want to give it a little bit of a push. maybe a centimeter per second or less, so a fraction of an inch per second. Change the speed by that much. And meanwhile, these asteroids are going around the sun at speeds of something like 20 miles a second. So you're going to try to measure the speed change of something that's going 20 miles a second and say that you're changing from 20 miles to 20 miles plus 1 inch a second. That's very hard to measure if you don't have another spacecraft sitting there. But the moon, so this is an animation of an asteroid moon going around an asteroid here on the right. Instead of 30 kilometers a second, these go around their main bodies only at maybe 30 centimeters a second, a foot per second or 2 feet per second. So you can change the speed by an inch per second or less and be able to measure that very easily. So the lowest cost way, and I know there's a lot of you American taxpayers out there, the most cost-effective way for us to do this test is to go to an asteroid moon and nudge the asteroid moon. So this is looking down kind of from near the North Pole of the solar system. That inner ellipse is the Earth's orbit. The outer ellipse is Didymos's orbit. And now this shows DART and DART's orbit, DART having just launched in this animation. DART's orbit stays very, very close to Earth. And basically, in a lot of ways, it goes out there and lets Didymos or Dimorphos crash into it. So it might be a charge if it were a basketball play. And the impact occurs a little bit less than a year after DART's launch in September of 2022. Here's the scale of the kinds of things we're talking about. DART itself is only about the size of a vending machine. And then its solar panels extend out quite a bit. So its solar panels are kind of the length of, each one is about half the length of a bus. So you put them both together and from wingtip to wingtip, it's a little bit longer than a bus. Dimorphos, which is the object we're going to hit, is about the size of one of the pyramids of Giza. And then Didymos, which Dimorphos is orbiting, is the scale of some of the largest skyscrapers in the world. But we're not talking about something like Jupiter or a galaxy, something that's unfathomably big. These are objects that are of pretty human scale. And since I know I'm talking to folks in New Jersey, I tried to find an appropriate part of New Jersey to compare this to. So here's Princeton University up here. Here's the area where the Martians invaded in Grover's Mill in 1938. And you can see that Didymos and Dimorphos are here to scale the size and their distance from one another, and they're really pretty close to one another. If they were sitting on Earth, you could walk from one to the other very easily, very, very quickly. So this is a much, much smaller system than spacecraft usually visit, and Dimorphos will be the smallest object visited by a spacecraft. We have 4 things that we need to do for NASA to consider us a success, which of course we very much want. So we will need to impact Dimorphos, which again, we plan to do. We need to change the orbit period by at least 73 seconds. Right now it's 11 hours and 55 minutes, I think. So we need to change that by at least 73 seconds. We need to actually measure the period change, because that's, science. You can't just do stuff. You got to measure what you did and try to explain it. And then the 4th thing we need to do is measure how the momentum of Dimorphos changed after we hit it with DART. I have a slide on this in a little bit, may even be the next slide, but it's not as easy, not as straightforward as one might think. So like I said, we're going to make measurements from Earth. Didymos and Dimorphos are very small, they're very close together, and they are never going to appear as more than a single point of light to our telescopes. We'll have radar measurements that will see them as 2, but all the optical telescopes we have is just going to be 1 point of light. So the way we're going to make these measurements is by watching the brightness of that point of light. And that brightness will go up and down as Dimorphos comes in front and blocks some of Didymos and throws its shadow on Didymos. And then as it moves back behind Didymos and has its light blocked by Didymos. And what we end up with is something called a light curve. I don't know if some of you are familiar with that. That's kind of shown by this bottom trace here, where the dips are due to Dimorphos moving behind and in front of Didymos. We've been making measurements like this for years and years. And that's how we know the period, the orbit period of Dimorphos so well. We'll come back after DART hits. We'll make these measurements some more. And these dips will change in frequency. That will tell us what the new orbit period is. And we will know that that change was because of DART. And then that will let us figure out this beta number. Beta is basically a comparison of how the momentum of Dimorphos changes compared to the momentum that the DART spacecraft brought it. If you have what's called a non-elastic collision, for instance, two ice skaters who collide and hang on to each other, then beta will equal 1, and the change in the momentum of Dimorphos will equal the momentum of DART. But we don't expect to have a collision like that. We expect to make some debris. That debris will carry some of the momentum and give Dimorphos an extra push. We have reasons to think that, there are computer simulations, there's experiments, there's lots of reasons to come up with lots of numbers that have a wide range, which is part of the reason we want to really do this experiment. It's possible beta will be 2, that the momentum that Dimorphos has will be twice what we bring in. There's some argument for it being 4 or 5. There's some argument that it'll be actually pretty close to 1. It'll be 1.1. So this is one of the science results that we're really looking forward to, because if we're going to use this technique, we need to understand, if you give an asteroid a push, how does it respond? And then these funny looking plots are generated by people on the team who work doing impact simulations. So this is a cutaway, basically, where the top part of each box is free space, and the bottom filled in part is down into the asteroid. You can see a crater forming and this ejecta, as we call it, the debris moving away. And depending on the nature of the asteroid and the beta that we pull out, that will tell us whether we have something that's more like that's more gravelly, that's denser, that has micro porosity, or although we don't expect it, no porosity at all. So I'm going to talk about the spacecraft a little bit here. We're carrying a lot of new technologies and testing those out, as well as testing out the technique as a whole. I'll talk about some of these in more detail in upcoming slides, but I'll just note that one of the things we had was a solar array that started out rolled up like a roll of paper towels and then unrolled in orbit. And that now that we've tested it, it's working great. That's something that can be used on future spacecraft and allow it to save room in the rocket and fly on smaller rockets, because it can kind of fit in smaller spaces. We're carrying a CubeSat built by the Italian Space Agency. This is basically a tiny spacecraft that's only about the size of a cereal box. It is the Italian Space Agency's first mission that's going beyond Earth orbit. So it's very exciting. The Italians are very justly proud of this. It has 2 cameras. One, they're Star Wars fans. One of the cameras is called Luke. The other camera is called Leia. One of them is a color camera. The other one is a monochrome camera, so black and white. The black and white camera has a little bit better resolution, so is a bit more zoomed in, and the color camera is a little bit zoomed out. We're going to deploy LiChaCube from DART about 10 days ahead of the impact, the DART impact. It's going to back off a little bit. It's going to move so that it doesn't hit and then it will fly by Dimorphos about 3 minutes after the DART impact and take images of what happened. And then after it flies by, it'll turn around and get pictures of the far side of Dimorphos, since DART is just on a one-way trip. And then over the following weeks, so into October and November, the pictures that LichCube takes will be downloaded to Earth. As you can see, it's very small, like I said, cereal box size, so the antenna on it isn't very big either. So the bandwidth is very very small. It's like those of us who remember the modem days. We know quite a bit about Didymos, the main body. We've been measuring, like I said, light curves of Didymos for years, using data like what we see on the left. So this is, a starry sky from January 2021. We've put a box around Didymos so you can see it moving across the sky, measure the brightness on each image, and pull out the light curve. Didymos was close enough to the Earth that there were good radar measurements made in 2003. So we have a good radar shape model from Arecibo, the late lamented Arecibo radio telescope. And then we also have been able to measure the composition of Didymos. For those of you that are not spectroscopists, you just have to take my word for it, that we have determined that it's a close match to what we call ordinary chondrite meteorites. These are very common meteorites. You can buy them on eBay. It's the same kind of object that fell on Chelyabinsk, actually. So it's a very, very common type of material that's out there that is the most common material to hit the Earth. So this is a representative test of what's out there. We don't know a whole lot about Dimorphos itself, though. We haven't had a lot of direct measurements of it. On the bottom here, you see a lot of the different shapes that the engineers went through in testing their systems, testing their algorithms. All of these shapes, except technically the sphere, have been seen in the asteroid and comet population. So it's not unreasonable to think that Dimorphos could be shaped like one of these. My money would be on this one, ID2 KW4b, but we'll see in a few months. So we're going to find out about Dimorphos using the one instrument carried by DART, and that's a camera called Draco. Draco is very much like the camera on board the New Horizons spacecraft, which is out at Pluto. It's also a lot like a camera that's being carried by the Lucy spacecraft. They're all built by the same folks where I work at the Applied Physics Laboratory. This is a picture of M38, which is not a very famous Messier object, but was the handy one for what we wanted to do at the time. So this is an image from space, from DART. Showed that the camera worked. We're all very happy about that. And Draco and DART will be detecting Didymos itself before too long, in just about a month. About a month ahead of time, we detect the Didymos system with Draco for the first time. And then there are these milestones that are, when we start getting continuous coverage and begin what we call the pre-terminal phase. At about 4 hours before the impact, we hand over the keys and hand over the steering wheel to our autonomous navigation system, which we call SmartNav. And SmartNav is what brings the DART spacecraft in for its hard landing. Like I said, we're coming in at 14,000 miles an hour. We're trying to hit something the size of one of the pyramids of Egypt and do it with something the size of a vending machine with two half a bus size solar panels on either side. So there's no way you could sit there with your Xbox controller and bring yourself in. So we've got the autonomous navigation to do that. And the images themselves up until the last minute are not going to be very instructive. Even 1 hour out, Dimorphos is still only just a little over 1 pixel in size. At 4 minutes out, the SmartNav gets its last instructions and makes its last maneuvers that are complete at 2 minutes out. And at 2 minutes out, Dimorphos is still only about 40 pixels across. At that point, SmartNav takes its hands off the wheel, and it's metaphorical hands off the wheel and its metaphorical feet off the gas, and we coast in. At 20 seconds out, we get images at 50 centimeters per pixel, which is required. So it's not until 20 seconds out that we get these images that we really need to help interpret what we're doing. And we will keep taking images until we can no longer do so. These are simulated images, of course. These are using the asteroid Itokawa, which was visited by a Japanese spacecraft as a stand-in for Dimorphos. We hope to get images as late, maybe as 3 seconds out, which would give us 9 centimeters per pixel on the surface. 9 centimeters is only about 3 inches. This again, this amazing scale, this amazing spatial resolution. So, like I said, we're coasting with DART for the last 2 minutes. Well, basically, it's the equivalent of, coasting when you're over the Indianapolis 500 and then coasting all the way to Baltimore and landing in Camden Yards. You can tell this is someone who works here with me, given his choice of Camden Yards. So it's 500 miles of coasting and hitting a small target. It was great to see this built. Like I said, if you want to, to get some insight into what spacecraft look like when they're being built, the next several pictures show that. Here it is. It looks like a vending machine. You wouldn't know it wasn't a vending machine at this point. It's a box with wires and components. This was all done during the pandemic, so people had to adapt usual practices to be COVID safe and to socially distance and use remote and virtual tests when they could. Here's the solar panel I mentioned. So here it's all rolled up. When it's extended, it's again about half the size of a bus. Here are the Italians looking very happy with themselves, as they should. They've just put LichaCube on the side here. So there you can see LichaCube bolted onto the side of the spacecraft. When the spacecraft was finished, it was literally put on a truck and literally driven across the country from here to California. The truck drivers only stopped for driver switch and to get gas. They did not otherwise stop. So they got across the country pretty quick. It was put on a SpaceX rocket. I think it was the first SpaceX launch beyond Earth orbit. Unless you count the car, but the car is kind of a weird case. And then it launched, and I was lucky enough to be there to see the launch. It was a beautiful night launch. We've been told that night launches, it's always foggy at this site and all that, but it was great. It was beautiful. And if you ever get the chance to see a launch, whether or not it's a rocket you're involved with, I heartily recommend it.
Falcon 9 was to get
because it was a SpaceX rocket, that meant that we got some coverage that people don't necessarily get for other planetary missions. We got to see them deploy it into space, and I'm not sure when in the video. There it goes. So we actually got to see it go. This will probably be the last we see of DART. Although since the intercept with Didymos happens pretty close to Earth, it's not impossible that some really, really powerful telescopes will catch it. I don't know if it's going to be 23rd magnitude or 22nd magnitude or 24th magnitude. I guess it's not impossible. Some pieces of it will survive the impact and be sitting in that system for the next spacecraft to come. This is a fraction of our team of scientists because, we talk about the mission, but missions are people, missions are made by people, missions are run by people. People are putting things together and analyzing the data. And this is a very international team because planetary defense is an international concern. Impacts can happen anywhere on Earth. I talked about the Chelyabinsk impact. Impacts occur on all continents. There are large craters that can be found anywhere. And there is a sibling mission to DART that the European Space Agency is going to fly called Hera. Hera will launch in 2024, and it will go to the Didymos system, and it'll follow up some of the work that DART does and make measurements that DART couldn't make because it's just coming in and impacting. So it'll measure the crater that DART has made. It will measure the mass of Didymos, of Dimorphos. It'll have two of its own CubeSats that will land on Dimorphos. So together, these two missions really are gonna do a great comprehensive look at what happens when you try to deflect an object with this kinetic impactor technique. So here's how you can keep track of us, kind of hitting the home stretch here. Of course, we have a website. We also have an outreach program, the Planetary Defender program. You can go there, take a short quiz, and get a little certificate saying that you're a planetary defender. We are present on social media, as you might expect. NASA basically runs missions now, social media now, but the Applied Physics Lab, the Johns Hopkins Applied Physics Lab, where I work, has its own social media as well. And then I have my own account, which sometimes does astronomy, sometimes does other things. You could also visit our outreach page, where you could, if you have a 3D printer, we have directions for making a printable model of DART or of Didymos and Dimorphos. For legal reasons, I have to say that middle thing is a toy bricks model. We have instructions for building DART out of toy bricks. And then there is a QR code that lets you kind of do an augmented reality experience. There's my friend and colleague Nancy Chabot posing with the real DART in the background over her left shoulder, and then with the virtual DART above her head. It's an astronomy group, so I thought I would put in some astronomy info here. When I'm not working on this planetary defense stuff, I am a planetary astronomer. I get my data at the telescope. So we thought we'd at least cover this base. With an 8-inch telescope, you will not be able to see Didymos through the eyepiece. This map here, this is an old Apollo 11 map, which was just about the best star map I could find for these purposes. That was in the public domain. The circles there show the Didymos system's path from the start of August, kind of off the left edge and then onto the right edge and moving left through the sky. At the time of the impact, it's pretty far south, but it's also pretty bright for an asteroid, 14th to 15th magnitude. And then it starts moving north through the sky. So for the purposes of the mission, we're using a lot of southern hemisphere telescopes around the time of the impact. Then we're switching to northern hemisphere telescopes. If you have a CCD or SLR, we think it should be that 60-second or less exposures would be able to at least show you Didymos, and if you want to see it streak. The maximum sky motion isn't super fast, so again, the estimate from Brian Warner, who's one of our colleagues, is that you should just be able to track with the sky, track sidereally, and that would be all right. So I guess it wouldn't really streak too much. So where is DART now? It is 41 million kilometers from Didymos, and it's closing on Didymos at 10.7 kilometers a second. So it's about 100 times the distance from between the Earth and the Moon. That's how far it is from Didymos right now. It's closing on the Earth too. The Earth and DART are slowly moving together. It's about 23 million kilometers from Earth. If you were on DART, you would probably want to get off of DART pretty soon. Earth is by far the brightest thing in the sky other than the sun. If you were on DART, it's at magnitude almost -6. It's about 1/3 lit, and it's in the constellation Coma Berenices. If you had 20/20 vision, and hopefully a lot of you do have 20/20 vision, you would just be able to see Earth as a tiny disk. At this point, the moon is about 50 arc minutes, so a little less than a degree from Earth, from DART right now. It's a magnitude -0.5, so it would be one of the brightest objects in the sky, but it would only just look like a moon. So here's just kind of to close here, we have a trailer. So this is a little over a minute, and it kind of is an animation that shows the DART mission start to finish. So here it launches, the payload fairing opens, and then we saw this video from, we saw DART actually come off of the spacecraft. Here the rollout solar arrays are rolling out. While still in orbit around the Earth, the camera opens, the camera cover opens. It leaves Earth orbit and starts heading on its way toward Didymos. It uses the ion engine, so we've tested the ion engine. Now time moves very fast. It's deployed. LiChaCube, we're only 10 days out. LiChaCube's solar panels open up. Draco acquires Dimorphos and guides it in. And then I think we have a discretion shot because none of us who work on this really want to see DART get destroyed. So we cut to black. And then we have the logo. So again, we reach our target asteroid in September 26th at 7:15 p.m. So early evening, no need to stay up crazy late and get caffeinated to do that. And I think you should certainly be able to follow us online at nasa.gov. I don't know if there are going to be television stations that stream it or not, hopefully, but certainly we'll be on your favorite, NASA sites talking about this, and presumably you'll be able to follow us at various other places as well. So I think that's my last slide. Yes. So I'm happy to take any questions you might have.
Well, I have one big question.
Yeah.
This strikes me as the equivalent of leaving Bar Harbor in your car and traveling nonstop to San Francisco with the hopes of getting a green light at a particular intersection. So how is it, and how is it that when you arrive there, that Dimorphos is actually a few hours ahead or behind, and it's actually behind Didymos? Could that happen?
Oh, so that's a great question. So so measuring the light curves of asteroids and pulling out the orbit period from of the orbit period of asteroid moons can be very, very precise, especially if you have years and years and years of data. So Dimorphos was first seen in 1996, and the precision on its orbit, we know that it's 11.92 hours or something, but we know it's not just 11.92. It's like saying pi is 3.14, right? It's 11.92, blah, 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 blah. We know the precision of Dimorphos's orbit to a tenth of a second or less. And one of the requirements that the mission had was just what you asked, was we need to know where it is, and we need to know where Dimorphos is to some particular precision to target it. And so the observers in the group, we have a dozen or 2 dozen astronomers said, yeah, we can do that, and went ahead and did it. We just got some data earlier this month. We had last observed it in March of 2021 and said, okay, here's where it's going to be when we next, see it in July of 2022. And sure enough, in July of 22, they said, yeah, here, yep, the light curve is still what we expect. It's where it should be. So,
well, now let's take it. Let's take it. But the launch, now you know it, but the launch, let's say the launch is delayed 10 minutes.
oh, I see.
Something. So now you're in there and you hit the rockets and off it goes. How do you control the arrival time?
Yeah, so there are so using your example of Bar Harbor and San Francisco, you do have a brake and a gas pedal. So there are times and so DART carries propulsion, and there are these things called trajectory correction maneuvers. So there are, we have folks who do the math, who say, okay, look, here's where it would be really convenient if you do the math and you do the physics. If we know by July 1st, 2021, that'll be a great time for us to make a change. I guess we launched in November 2021, so that's not a good date for me to use. If we know by August 1st, 2022, if you can give us an update on August 1st, 2022, then we can tell, we can fire the rockets and slow down a little bit or speed up a little bit and make it work. So you get these milestones and these times, and basically what, again, to use your metaphor a little more, you've got someone sitting in San Francisco who's timing the lights and radioing ahead and saying, guess what, I still think you're okay, but maybe once you get to Reno, take it up to 72 miles an hour instead of 70.
Are there any questions here at the observatory? We have a full house. There's got to be one question. There's a hand back there, or somebody was just waving me off. Don't ask me. All right. Well, we got a couple of questions and we're going to wrap up here. With regard to the CubeSat, when it's left, its mission is to, after DART impacts, it's going to be monitoring. I didn't see any antennas on that little guy. How is that communicating?
Yeah, it's job. So the trick with all of these missions, right, is that you're coming in at some speed, and then if you want to stick around, you need to take that speed out. So DART is coming in at 14,000 miles an hour. LiCiCube is hanging out, also going 14,000 miles an hour. It's going to move a little bit, so maybe it'll be going, a little bit less or a little bit more. But if it wanted to stick around the system, it would need to have some rocket that took the 14,000 miles an hour out. It doesn't. So it's going to scream on past just a little bit later. It has a tiny antenna. It's not a big thing like DART or other spacecraft has, but it's got a tiny antenna that fits on that serial box. And so that's why its downlink rate is very small. So
Okay.
it's sticking around close to Earth. We think that it's going to be able to send down 1 or 2 images a day. And eventually it'll get all the images down. And then what the Italians do with it is up to the Italians. I think that it's likely that they'll get some engineering data and some sorts of things so that when they launch their next spacecraft, they can use what they've learned. But yeah, it's just it's gonna be close to Earth, and then their orbits will diverge, and then it'll just be out in space.
Wow. All right. Thank you. Are there any other questions for Dr. Rivkin? We want to certainly respect your time this evening and appreciate your presenting for the audience here. Any questions? Yes, sir.
So, why do you want to push that asteroid?
Why do you want to
To push that asteroid?
approach the asteroid? Push it. The question is, why do you want to push the asteroid?
Yeah, it's a good question. So we think that we think that there could be times when asteroids are going to come and hit the Earth, and we think that a way to stop them from hitting the Earth is to just give them a little nudge, a little push, because that push will change their orbit and make it so that they miss the Earth. So this is a test of how well we can do that, both from kind of the science of what happens when you push an asteroid, and then also the engineers, saying, look, we want to test the smart nav. We want to test that we can come in at 14,000 miles an hour and hit something that small. So that's why we're planning. That's why we'd like to do it. Does that your question?
Does that answer your question?
Yeah.
Yes.
And then I also have
Great.
two
Sure, please.
questions.
Mhm.
Why is everything start with a D? Didymus, Dart.
That's a great question. Why do all the names start with D? Didymus, Dart. Is there some synergy there we don't know about?
Oh, yeah, that's a good question. So Didymos means twin. Didymos was given that name because it's because it has a moon, because it's a double asteroid. Didymos means twin in Greek. And the people who discovered the moon, when it came time to give the moon a name, they wanted the name to sound like Didymos and to have some meaning. So Dimorphos was named by a Greek member of the team, so it's still Greek, and it means having two forms. It recognizes that we are changing the surface of Dimorphos by hitting it, so it had an original form and then the form after we hit it. So those two are similar on purpose. Dart, that's just luck. That Dart starts with a D. There's nothing more to that.
And you had another question too?
Yeah. How do you control when the camera opens and when the solar panels fan out?
He's asking, how do you control when the camera opens and the solar panels fan out?
There are commands that can be given. Basically, you can control, right? Lots of people can have things now. They can control their garage doors with their phones, or turn their refrigerators on from their phones. It's the same general idea. We use radio communications from the Earth, and we send commands out to these appliances. A lot of the electronics is not necessarily that different, but instead of saying open the garage door, we're saying take a picture, or we're saying start your rollout sequence. The cameras are digital cameras, and while some of the specific commands might be different, a lot of the general electronics is and the general computing stuff is not too unlike what people use for other things.
Okay. Great questions. Yes.
How long does it take for Earth to communicate with the satellite and for the satellite to communicate with Earth?
Did you hear that? How long does it take? Okay.
Yeah, I did. So the communications is at the speed of light, and that's from the animations you saw that everything's kind of moving, and so at the time of the impact, I think it's 37 light seconds away. So it will take about that much time, 37 seconds to send a command, 37 seconds for the pictures to come back. The Draco, this isn't what you asked, but may also be in there somewhere. Draco will take an image every second. So it will take an image, put it through its processing, send it out. we don't think we're going to get an image that's taken just 1 second before the impact, because it has that extra stuff to do. But it will be taking an image every second and then going through the electronics and preparing it and putting on a header and sending it out. And then we will presumably stop hearing from DART 37 seconds after it hits.
There was another question here. Yes.
When will we know the answer for the beta, or what the results are? When will the general public know the result of this, of DART?
Okay, so the question was, when will the general public know the results from DART?
Yes.
I have a several part answer to that. Part one is it depends on it to some degree. That's up to the asteroid. If beta is 5, then the change in the orbit is going to be very large, and it's going to be obvious pretty quick. Just because we've made such a big change. Some of the radar measurements might be able to see that big of a change very, very soon after. There will be, I'm sure there will be a press conference the day after the DART impact that at least talks about some of the first things. Here are the pictures. We're going to be streaming the pictures, so I think the pictures will get there anyway, but maybe some very quick analyses. For something like beta, to some extent that will be up to NASA and when NASA wants to talk about it, but we are planning some presentations at scientific conferences in December, and then all the publications we have been open, not open source, open access, so the public can already get to the scientific results we published so far. We anticipate, we intend to make all of our results also open access. So whether there are interim things in between the DART impact and that conference in December is probably going to depend on what we find, and then up to how NASA wants to come out with it. There's going to be JWST, at least we're planning to have JWST measurements, both at the time of the impact and in November. So same sort of thing. If the JWST folks decide that they want to show their pretty pictures, hopefully pretty pictures of Didymos, then that will have to be worked with them.
That'd be very cool. Any other questions? Yes.
If DART missing the asteroid, could it be a threat to Earth?
If DART misses the asteroid, could it be a threat to Earth?
No. Whether or not DART misses or hits, we will not change the orbit of the system, and we are hitting it from a direction so that Dimorphos moves a little closer to Didymos, and that, if anything, the system moves a little further away from the sun. We've absolutely been thinking about that from the very start. We are not going to make this is not going to be a danger. It's not currently a danger. Someone independent, someone who's not on the team, published a result that maybe there'll be one extra shooting star. I started the talk with the shooting stars, maybe one extra shooting star over the course of the next 50 years or something, but we're not going to make this into a danger.
Okay. Any other questions? Yes.
How does DART detach from the camera?
How does DART detach from the camera? Are you talking about the little CubeSat that comes off? How physically does the CubeSat come off? Is it exploding bolts? Is there a little door
spring,
and it gets a spring?
Yep, door opens and it's a spring, and the spring is, at least I believe, the spring is calculated. So in your physics class, pay attention in your, I forget which physics class it was, but you've got a spring constant, and they push push the spring down however far to get whatever force they want to make Leacha Cube go the way it wants. I think Leacha Cube also has a tiny rocket, a tiny amount of propulsion, so it can push itself where it wants to a little bit, but it's mostly a spring that's doing that. We don't want Leacha Cube firing its tiny rocket close to Dart, no matter how tiny that rocket is.
Simple is always best. Any other questions? Yes.
I have one.
Oh, please, go ahead.
Would you, I assume you're hitting Dimorphos head on rather than on a receding side of its, oh, okay.
Yeah, we are hitting it head on. It turns out that it's not that big of a deal in terms of the results, because Dart's coming in at 14,000 miles an hour, and Dimorphos is moving at like 6 inches, at 6 inches a second or something. So we do get a little bit extra bang for our buck by hitting it head on, but not that much.
Okay. There's a question here.
Yeah, sorry. I'm not sure if you mentioned it. When did you guys start building the spacecraft in the first place?
When was the start the build? Did the build start for the craft?
What was the timeline to get it built?
How long did it take from concept, design, engineering, approval?
Oh gosh. So in terms of the first idea, my colleague Andy Chang at the Applied Physics Lab with me was first talking about the idea 10 years ago. And then I think there are pictures. I think these have dates. Yeah. So this is July 2020. So this is what the spacecraft looked like just 2 years ago. The idea was 10 years old, and then we kind of worked on it and kind of kicked it around for a little while. We started getting, or NASA started expressing interest in it in 2015 or so, and then I might not be remembering these dates quite right, but I think around 2017, 2018 was when we kind of got the go-ahead from NASA. But the way these missions also go is that you get a go-ahead from NASA, but they certainly reserve the right to say, we don't like how this is going. We don't think you're spending the money right. We don't think this is going to work. So it was probably not until 2019 that we got the final, yeah, okay, we're happy with all of this. Not that they were unhappy before, but they right, you go through these different reviews and you go through these different gates, and so it was 2019 or so, 2018, that we got that go ahead and start building things, go ahead and start buying the pieces you have to buy.
Okay. Yes.
In case the mission fails, is there any other plan to use the other options, like nuclear power or something like that?
Oh, well, so this is so I'll the T in Dart is for test. So this is not there's not any reason if Didymos dodges a bullet, there's no reason other than spite to go back after it. So or Dimorphos, I guess, not Didymos. Depending on, and then in terms of, if Dart were to miss, certainly we would want to understand what happened, and then use what happened as a way to make sure that the next test is a successful one. But the nuclear deflection test, I think, is not in the cards. It's just not. It would break the nuclear test ban treaty or the outer space treaty or one of those. There's even some legal opinion that if something were coming in for real, it's not clear that we could legally deflect it. Although people certainly would, if that was the only option, people would do it and deal with it later. But testing a nuclear deflection is just not. It's just against international law. They're not going to do it.
One last question for this evening. We'll let the, yes, please.
What's the most expensive part on DART?
The most expensive single part.
In all the years we've
you
been
know,
doing this,
probably-
nobody has ever asked that question.
Yeah. I don't know if this is fits in your definition, but the rocket, the SpaceX rocket was the single. Now, whether you count that as a single part or not, I don't know. Otherwise, probably the camera. Again, if you count LichaCube as one piece or not, maybe LichaCube, but LichaCube has other parts, so it kind of gets into a funny, like, what's a part, what's a piece. So there's my hedge.
Okay. Dr. Rivkin, we want to thank you very much for presenting this evening. It's very, very informative. We're going to actually take those dates and get our cameras and telescopes observing for the event too. So thank you
great.
very much. We appreciate you being
Thank
here.
you.
Round of applause for Dr. Rivkin.
Thank you for having me, and yeah, please visit the websites and follow along with us. And we're happy to do this, and happy to help do our little part to
All
save
right.
the earth, I guess.
Thank you again. All right.
Thank you very much.
We appreciate it. Thank you very much.
Bye now.
Bye. Before anybody gets up, could we turn the lights on in the back, please? Somebody hit the lights back there. Just turn them all on. There you go. Wow, that was great, right?
Yeah.
Hey, very informative. Where's our QOs for this evening? Is the dome open? What's the status of the sky? Where's our staff QO this evening?